Now, can you hear me? Good. Somebody says they can hear me. I'm going to go with that. Now, where was I? There. Oh, come on. Okay, back to you guys. What are 5 things that you learned about lean manufacturing? Or what's one of them?
We got some basic things. One of the big things is to eliminate waste.
All right, so lean manufacturing is about eliminating waste. What else did you learn? Let me get another table. What's something you guys learned that was not eliminate waste?
It originates from Toyota's business model.
Toyota, what's something you guys learned about lean manufacturing that's not about Toyota and not about eliminating waste? Well, it might be about eliminating waste, but something more specific than that.
The process focused on reaching efficiency.
So focused on reaching efficiency in processes? Okay. Back over in the corner. What's something you guys learned about lean manufacturing? Over in the corner. Yeah.
One of the 8 ways of lean manufacturing is like overproduction. So like, if a certain part needs to be torn to 3/1000 of an inch, 2/10 of an inch, or like torn.
Okay.
Is a waste that you're taking the time to do.
So I think I got it. So this overproduction that you're talking about means making more part than the customer asked for. Like so it might mean back like the second day of class, we talked about quality, right? So it might mean making more quality than the customer is expecting. So overproduction. Because a lot of times when we intuitively think, if I said what's overproduction, I think everybody would guess that we mean making too many things, right? And so that's also a kind of waste that we might want to eliminate. But overproduction in the sense where you're making stuff the customers don't care about. What about you guys? What's something you learned?
That it helps reduce inventory costs, that's increasing profit.
All right, so one way that we might eliminate waste is to reduce inventory because it costs money to have inventory. Is that it? Yeah. And so if you think about this, so if you're going to have inventory, so inventory is stuff that you made for the customer, but you haven't sent it to the customer yet, maybe because the customer hasn't asked for it yet. I had years ago, right after I had my first machine shop, and I got my first new customer that wasn't one of the customers that sort of came with the business when we bought the business. My first new customer, and it was a cool customer because they make parts for sailboats and stuff like that. And I have a sailboat. I like sailing. And they actually were making a part that was going to go on every America's Cup boat that year. It was required by the race committee that they had this particular part on there. And I was making a component of that part. So I was a tier 2 producer for that. It was really cool. And so they said, well, right now we need 10 of them. but we're going to need 100 of them by the end of the production run. Yeah, I said, great. And so the part required some anodizing, so a secondary process. I didn't have the capacity to do that. So we machined up the parts, and then we sent them out to the anodizing place. And when you do anodizing is when they put this coating on the aluminum parts, there's a minimum lot size. So the minimum charge that they would give us was for like 200 parts. So even though I only had 10 pieces, I had to pay for 200 pieces because that's their minimum charge for doing that process. And so that was great. And so then my customer orders 10 more. And I'm smart this time. I know what the minimum is. And he said, hey, we're going to order 100 of these by the end. Seems like a good idea to have some inventory. This would be a good business decision to have some inventory at this moment. So I go ahead and make 100 of them. Send them off to get anodized, bring them back. I ship 10 to the customer because that's how many they ordered. And in my garage right now is a box with 90 of those parts in it. And for some reason, I couldn't just throw them away. I don't know why, but in a box in my garage is 90 of those pieces because they never ordered any more. I don't know if they changed the design. I don't know if they went with a different producer, but inventory costs money. Sometimes it costs ego. All right, so inventory is a thing. We'll double check on our friends at home and see if they have any comments, just that they can hear us. Okay. If you guys have any things you learned about lean manufacturing, you want to type it in the chat, go ahead and do that. You guys did inventory, right? What do you know about lean manufacturing?
So I got that around 30% of the United States energy goes to the manufacturing.
About 30% of the energy consumed, so like electricity consumed in the United States, goes to manufacturing. That's something I didn't know. Anybody know what the percentage of GDP is manufacturing in the U.S.? You guys know what GDP is, gross domestic product? If you take up sort of the combined value of everything we made and did in the United States and jumped it all together as if we were one company, then that's the GDP. Anybody know what the percentage is? Somebody look it up. Yeah. $2.27 trillion is attributed to manufacturing. Yeah, does that have a percentage of GDP? What's that? 10.8% of the US GDP is in manufacturing, consuming 30% of the energy. So it's expensive, I suppose, energy value. That 10 point whatever, that number's kind of low. Is the transportation industry, is there a number for transportation industry? How much of that transportation is moving manufactured goods that wouldn't need to be moved if they weren't manufactured? In retail sales typically sells things that have been manufactured. Now, not all of it was manufactured in the US, but that 10 point whatever percent number is actually pretty low about manufacturing, but that's not the topic today. Lean manufacturing, right? That's when we, lean manufacturing is like when you go to the factory and it's a really windy day and everybody's got to lean in. No. So I heard some people giggling over here. Those sort of suppressing, was it a suppressed laugh or a suppressed groan? What did you guys learn about lean manufacturing?
It's important to design out inconsistencies.
So if you want to do, yeah, all right, so design out inconsistencies. I haven't called on your table yet, have I? What did you guys learn about lean manufacturing?
So in lean manufacturing, they kind of look at waste from a general standpoint as anything that doesn't create value for the customer.
All right, so this is key because we said here at the top, the very first thing that anybody told us was that lean manufacturing is about eliminating waste, right? And you have defined waste. So let's do it again. What is waste? Yeah, but you said it much better when you started. So go back to the beginning. Eliminate anything that does not create value to the customer. So waste is anything that does not Why are you going to disconnect? It appears that I have left the room. Huh. Let's see if it actually disconnects. Look at that. I guess I shouldn't have left the room right in the middle of class like that. One, 4, 1, 6. Back in the room. Look at that, back in the room. Funny story about that auto disconnect. So if your computer's wireless signal is detected to be more than a certain distance from the room, it's supposed to disconnect. Funny story, they didn't always have that. In fact, when this term started, they didn't have that. And on Thursdays, there's actually a Zoom meeting that I'm supposed to be in that starts before this class is over. And so as to not waste time, what I did on Thursdays was close the lid on my computer, walk outside, sit down at a table, open the lid on my computer, and log into my Zoom. Funny story. The person doing the class after us said, I started doing my class, and then suddenly somebody else's computer screen was showing. So when I closed the screen, it showed like nothing on the thing. But when I opened it back up, it reconnected. Oops. Funny story. Lean manufacturing, that was not very lean, right? Value or waste is anything that the customer doesn't want, care about, need. Pick the verb, or pick the word there. You guys went first. Did you tell me anything that you learned? I can't remember if I asked you. Though you did give me a GDP.
I said there's a big emphasis on just-in-time manufacturing.
Just in time. Just-in-time manufacturing is a thing that is all right. So, what are some other things that are on your list of 5 things that we haven't talked about yet? Yeah.
Lean manufacturing does, it pulls demand with supply.
And so when we're doing pull manufacturing, it's when let's say you're making an assembly line to make M1800 thermoacoustic engines. And you're doing the assembly step. We're doing the assembly step. Now you're doing the base. You're making the base on the CNC machine tools. And you need to make a base. Yeah, you're making the base, and then somebody else is doing the assembly. All the other parts are already made, let's say. Let's say we have inventory for all the other parts. So you're running the machine that's making the second operation on the base, and you're running the machine that's making the first operation on the base. and you're running the machine, the bandsaw, and you're cutting the pieces so that they can go to the first machine, so that they can go to the second machine, right? And so there's a process here, right? You take the long stock material, you put it on the bandsaw, you chop it, goes to the first machine, then it goes to the second machine, then it goes out for assembly. That's the process, the steps that we're doing. So in a traditional non-lean or in a push system, you guys do your bandsaw work. You make a piece on the bandsaw, you send it to you guys do the first operation because you've got a piece. You send it over to these guys. Now, the second operation took longer than the first operation, right? Is that true? If I recall correctly, second operation. So when we do that process, you guys keep cutting on the bandsaw as fast as you can. The bandsaw cuts faster than the first operation does. So what's going to happen is there's going to be a pile of partially made parts waiting at the first mill. And there's going to be a pile of partially made parts waiting at the second mill. And let's say your process takes 6 minutes. So every 6 minutes, a part's going to come off that second mill and it's going to go to assembly. Does that make sense? What happens when you got to change tools on your machine? It's your machine. What happens when you have to change tools? Does the pile get bigger? You're gonna pause. You're gonna even stop the operation. The pile's gonna get bigger, right? Does the customer want half-made parts? Any customer want half-made parts typically? Typically no, right? So those half-made parts actually have no value, but they do have a lot of cost. What happens when there's a big pile of half-made parts in front of your machine? You're changing the tool, and I walk over and I kick bump into the cart that has the pile of parts, and they fall over all over the floor. And we spend more time picking them up. Maybe some of them get damaged. Maybe it gets probably not that particular part, but you could imagine that when parts get knocked on the floor, sometimes they get damaged. Sometimes they get lost. If it was steel, it might get rusty. So that's a push system. In a pull system, when assembly says we need a base, you make a base. But when you're making that base, you ask them to make you another piece of stock. And then you ask them to give you another piece off the bandsaw. So we're actually not running the bandsaw until you need a new piece of stock. And so you don't need a new piece of stock until the one you have goes in the machine. So when you put the one you have in the machine, you ask for another piece of stock. And when you put the one you have in the machine, you ask for another piece of stock. And then we don't have any half-made parts except for the one that's flowing through the system. So that if we scrap the part, we just scrap that one part that's flowing through, or whatever, however many machines, right? Might have 5 parts in the system if we got 5 different machines going. So in a pull system, and so that's more efficient because we have a lower chance of wasting the half-made part, right? We have, and I don't know if you've been to the machine shop over in Washburn, Manufacturing Labs. We're not very good at warehousing stuff. Stuff gets lost because it gets put in piles and moved around and stuff like that. So we try to do that here. If I were going to use a pull system for the labs, what would you do? If you were going to picture the students as the work pieces moving through the production system now. Because you can do that, right? You can use lean manufacturing tools to design anything. So we just made an example of designing a pull system for making those parts for the Stirling engine. But what if I wanted to design an ME1800 lab? The students are the work pieces, right? We're doing work on you. So how would we set that up? Yeah. All right, so, well, we do have a constraint, right? We only have so many machines. It would be ideal if you guys could all go to lab at the same time and all be standing in front of a cell where there's a mini mill, there's a lathe, there's a computer, and you could be there and you could learn everything all sequentially, right? That would be the ideal system. So if there's 18 students per lab, if we had 18 machining cells, that'd be cool. That'd be a lot of fun. Actually, it was similar to that when I did M1800. They had little cubicles. I think there was six or eight little cubicles. Each cubicle had a mill and a lathe in it and a TV monitor. And there was supposed to be a VCR. And they thought that we would go in and we would watch videos and we would learn how to operate the manual mill and manual lathe in a little cubicle without anyone being able to see us. The machinists that were in charge of the labs did not install the VCRs. I think by the time I even took the class, the TVs were not on the brackets anymore either, because they were worried that we would get ahead of ourselves and get hurt. They also ran around really fast looking at all the cubicles all the time to make sure that nobody was doing something stupid. That system might have worked if they just eliminated the walls so that the machinists could see everybody at once, right? Could have worked. Similar to what we do now, right? We have you go over there. So let's look at this. If the student is the workpiece, there's value added when the student's learning, right? And we said we want to eliminate waste, meaning we don't want to do anything that the customer doesn't want. Like watch the professor set up the projection equipment. Was there value in that? No. Right. So if you're the student, so what's something that would have value to learn in the lab? Yeah. So how to operate the machines. So what are the key steps to operating a machine? Yeah. So we've got that safety checklist we have you guys do as you do it. And so it might be the steps on that safety checklist. So what are those steps then? So what are the things that we want you to learn as you're doing it? Yeah. So the first thing we want you to learn is that it's important for you to know what the machine's going to do before you press the green cycle start button. We decided that it's important for you. Why is that important, by the way? Yeah. If everything's set up right and it all works right, though, nothing's going to crash, right? So it's important because, well, because I said so. I'm the rule maker guy. No, it's important because if you're operating for the first time, if you're making this part for the first time, it is entirely possible that you made a mistake setting it up, right? Especially if you're an inexperienced operator. It's entirely possible that you made a mistake, or it's even worse that somebody else set it up and then you arrive. It's entirely possible that they knew they didn't finish setting it up, but they forgot to tell you. So these things happen, right? So for you to have any basis to stop the machine before it crashes, because we want to avoid the crash, right? If you're going to have any basis for stopping the machine before it crashes, you've got to know what to expect when the machine starts to move, right? So that's why we always simulate in the CAM software. Now, it's possible to write the code that goes to the machine by hand. I mean, when I first learned how to program CNC machines, it was by calculating the points that the center of the tool had to go to, and then writing the code manually to tell it go from here to here to here to here to here, so that it would make a shape like this, right? So you got to program the center of the tool for where you want it to go. And so you could write that code by hand. Now, if somebody wrote code by hand to do that, could they simulate in the CAM software? I mean, when you're writing by hand, what is the CAM software? It's your head, right? It's your mind. But can we meet the need of simulating the CAM software? The purpose for simulating the CAM software is so that you know what the machine's supposed to do. If you wrote the code by hand, you probably know what the machine's supposed to do, right? So you do that. All right, so we wanted to simulate in the CAM software. And so how do we teach you how to simulate in the CAM software? by asking you to do it every time you get to the machine, right? Or watch the video, right? So we have that repetitive thing. So, but, all right, so the way the pull system there works though, what are you doing before you go to the machine? Because if we had 18 machines, we could just have you all step through the steps all at once, right? We don't have 18 machines. So we have you guys sit in the classroom and work on the programming, right? The writing the code in the CAM software. And then somebody comes and gets you and brings you to the machine. And typically, unless you're the first person in that lab to go, the person that's stepping you through the instructions is the person that just finished at the machine, right? So that person gets to see the thing twice. And then when you're done doing it, you teach it. When you're done teaching it, you go back to the classroom. The classroom is our buffer. And then we pull you out to the machine when the machine's ready for you, right? We don't send, when it's working correctly, we don't send you to the machine before the machine's ready for you, right? Sometimes it's not working correctly. But anyway, so we thought about this pull system thing when we were designing how to do the M1800 labs. We didn't have to do it that way, but that's what we did. So something else about lean. Anything else? Anything that jumped out? Something that's important that we haven't talked about? What we mentioned was these things like pull systems. So we talked about pull systems, designing out inconsistencies. I'll get more in depth on that. We want to eliminate waste, and waste is anything the customer doesn't want. Just in time. I think this problem is because this cable that's connected to the camera is not very good. And I think when I bang on the table, sometimes it gets loose and jiggles. I think so. But I'll try not to do that. All right. And we talked about Toyota, focus on process efficiency, overall production inventory, and it's a bad day to be the president of the AV club, huh? Anybody here in Lenses and Lights? No, so none of you can help me? One term, I had a student in the class who was a work study in the ATC. And every time something was wrong, they immediately knew how to fix it because they were the person that got sent out to classrooms to fix stuff when it was wrong. Okay, anything else that jumped out? I had everybody learn 5 things. We didn't write down that many things yet. Anything else that jumped out about lean manufacturing that you found was important? Something you'd be proud to tell your parents at 4th of July.
I would say that there's just more likely to be safer work environments with the fact that you can just tell when something's out of place because it's a lot more straightforward on how manufacturing is done.
So using lean manufacturing adds to the safety of the workplace. So do we know lean manufacturing now? When you guys Google lean manufacturing, how many, like if you just type Google lean manufacturing, how many hits were there? Like 13 billion, something like that? I think last time I did it and I wrote it down, it was like 13 billion things in like half a second. In half a second, Google found 13 billion things that talked about lean manufacturing. People talk about lean manufacturing, right? That's something that we can learn by Googling it. We can learn just the fact that there's so much there. So if you, anybody watch a YouTube video about lean manufacturing when they Googled it? No? See, I'm a video guy. I totally would have watched the video. Would have learned me something from the video. By the way, there are some really good ones. But what is lean manufacturing then? So lean manufacturing is, right? Oh, shoot. We're going to go over problems too. I promise you guys we're going to go over problems in the end of class. All right, lean manufacturing is focused on, it's nothing special. Oh, the Toyota thing? So what we call lean manufacturing in the US today is based on the Toyota production system, yes. The people that wrote about lean manufacturing, when they asked Mr. Toyota, a reporter asked him, how did you come up with the idea to create this fabulous Toyota production system that all this lean manufacturing is based on? You know what he said? I read Henry Ford's book. Right? He actually went to Ford's Ford factory to learn how to better make cars, and then he just codified it. He just systematized it and wrote it down in this system. So yeah, so lean manufacturing, yeah, it's based on this Toyota production system. And there's things like there's all kinds, and if you Google it, you'll see that there's all kinds of buzzwords about lean manufacturing. And we like to use Japanese words when we talk about lean manufacturing topics because of the Toyota production system thing, right? And we have 5 S's where it's you can look up the 5 S's, but it's about that safety stuff. It's about having a clean work environment. It's about having all the tools that you need to use at the location where you need to use them. So you don't have to walk around and go find the next tool. It's all these things, and you can get a black belt in lean manufacturing, right? There's people sell courses. You can become, but it's all common sense. It's all, don't do things the customer doesn't want to pay for. And think about that. So there's a whole toolbox of different things that people have figured out about how to do this. If you're designing 2 parts that have to fit together, design them so that it's impossible to put them together the wrong orientation. That's called poka-yoke. I think that's a Japanese word that means it's what you do before you get to the pokey stop, I guess, right? But it means design things so that they can only be assembled in one way. So yeah, that's lean manufacturing in one sentence. And remember, why we do this is because we want to make a profit, right? And profit equals value minus cost. And so lean manufacturing tends to focus on the cost side of this. It tends to focus on reducing the cost to do the manufacturing and without reducing the value. And so the value is what it's valued by the customer. So that's lean manufacturing in a nutshell. Sorry it took us so long to get started. Somebody had a question about the last 2 problems on the exam, or on the fake exam homework quiz thing, whatever we call it, mid homework quiz term thing. I don't remember which ones are the last 2. Could you tell me what the problem is? So it's about cutting force. What about it? There could be a lot of things about cutting. Okay. I think I know which problem it is then that you're talking about. So that's pretty easy to set up in a theoretical sense, and then I think you guys can solve it. So in our lathe, we've got our workpiece here, right? And we've got the chuck clamping it here and spinning it. So it's rotating this way. And we've got a tool here that's feeding this way, right? So the cutting force is getting applied here at that chip interface. And so for the purpose of doing this problem, we want to assume that 100% of the cutting force is being transmitted into the workpiece and trying to make the workpiece move in the fixture. And so if we look at the face, the head-on view of it, so there's the end of our workpiece. And if it's a 3-jaw chuck, I think that's what the problem says. And so these chuck jaws are interacting with the workpiece. And you could machine the jaws so that they've got more contact area and stuff like that. But the chuck jaws are pushing on the workpiece, right? And I think we told you probably a hydraulic clamping force. We told you how much we're squeezing with our hydraulic pump. And so there's this force in like that that's holding the workpiece, and what keeps the workpiece from moving in the fixture is friction, right? So friction keeps it from either rotating in the fixture and stalling or pushing into the fixture and sliding back, right? So it's friction. And so what's the friction force that we're, how much friction force is possible? So we'll call this force N for normal. Right, and those all have to be the same as each other, otherwise it'll accelerate. So friction equals mu times N. So that's how much is possible, but we're spinning the chuck, right? So it's rotating this way. And as we rotate, these want to accelerate out from their own inertia, right? Anything we spin around wants to accelerate away from the center of the rotation. So they're trying to accelerate out away from it. And so how much are they trying to accelerate out? What's it based on? Physics, right? What do we call that? Is it centrifugal acceleration? And then is there a force that results from centrifugal acceleration? What do we call that? Sure, or some people call it centripetal, I don't know. And then some people say you can't use one word, you have to use the other word, and I don't care that much about the word. You know what I mean, right? So what is that force that gets generated as the part spins around? It's based on the inertia, right? Anybody know what the equation is? Anybody have Google in front of them? So I said, what's the max? The question is, what's the maximum cutting force, right? And so the maximum cutting force is going to equal N minus whatever you calculate for that centripetal force or centrifugal force. So subtract the force that's trying to pull it apart, and you need to know the velocity, right? You need to know the speed. You need to know the speed, you need to know the mass, and you need to know the distance from the center, right? And I think there's a half and something squared in the equation, right? There's a half mv squared or something like that in that equation.
What I can see is mass velocity squared over radius.
Yeah. So then whatever you get for this friction force is going to be the maximum cutting force that you could have. What's the other problem that people had a question about? That was one of the two you asked about. What was the other one? So similar problem, right? The question is, so if you in a manual lathe, we often have a manual chuck that squeezes the jaws in and out. And there's a chuck key that goes in there, and you turn it by hand. And as you turn that, it makes the jaws come in. Turn it the other way, it makes the jaws come out. So if you've ever used a hand drill, it's similar to the chuck key on the hand drill chuck. Unless you use the one where you squeeze it with your hand. So if that is sitting on top of the lathe chuck, and you start the spindle, if it rotates around, it gets all that velocity from the rotation, right? It gets all that velocity from the rotation. So let's say it makes it around one time and it gets up to full speed before it comes out. Because there's nothing holding it in except when it's up on top, nothing holding it in really except gravity and a little bit of friction. So as it spins around, it comes out. And so the question is, how much energy is in the chuck key when it hits you in the forehead? Because it flew out of the chuck. And so to solve that problem, you'll need to know the mass of the chuck key, right? You'll need to know, because it all comes down to that force and acceleration again, right? But instead of how much is it trying to pull it out, we're looking at how fast is it going, because we need so what are the units for energy again? What's that? 1/2 mv squared. I don't know. What are the units for energy? Joules. And what's a joule? If you were to break it down into units that could be multiplied together to make a joule. What's that? The Newton meter? Newton meter. And what's a Newton? Meters per, did I write it correct? And so we need kilograms, mass, meters per second squared, acceleration, right? Times meters. So we need to know what's the acceleration of it. Okay, so you can figure that one out just by canceling the units. Also, I'm pretty sure there's a YouTube video where I go through solving it. Both of those last two problems, I'm pretty sure there's a YouTube video that's just me solving that problem. Anything else? I'm going to let you guys get to class. Again, if you have more questions about the quiz thing, we'll do this again at the end of class tomorrow, and I'll try to stop sooner tomorrow. All right.